turn. So last time we discussed the equivalence principle, which formed the basis for general relativity. And then we started discussing curved geometries, geometries that aren't Euclidean. So today we'll continue with the discussion of curved geometries. And then we'll move on to a description of what's called the FRW universe, which is a model for universes on scales larger than 100 megaparsecs. So we'll describe heuristically structure within 3D. And then we'll see how to measure distances in a curved spacetime. So that's the plan. So you'll recall from plane geometry that if you have a triangle, the sum of the interior angles is pi. But this idea is really only applicable to triangles you draw on the plane. So on a positively curved space, a sphere for example, you draw a triangle such that you go from one of the poles to the equator. So the meridians intersect the equator at a right angle, and there's some angle here. So on a sphere, the sum of the angles is bigger than pi. And finally, you can imagine saddle-shaped geometry. You draw a triangle on this guy, the sum of the interior angles is less than pi. So those are the three kinds of geometries we'll study. We'll study flat geometries, we'll study positively curved geometries, and we'll study negatively curved geometries. And when we introduce a parameter, kappa, to keep track of this. So in flat geometry, kappa will equal 0. In positively curved geometry, kappa will equal 1. Negatively curved geometry, kappa will equal -1. So that's a contract of the kind of space that we're looking at. So you'll remember as well from plane geometry, Pythagorean theorem, we have del x, del y, and ds is going to be equal to dx squared plus dy squared. So if you're looking in coordinates on a, so we'll have this, so if we're looking at in circumpolar coordinates, x will equal r cosine theta, and y will equal r sine theta. So dx is dr cosine theta minus r sine theta theta, and dy is dr sine theta plus r cosine theta theta. So if you write ds squared, this is dr squared cosine squared theta minus 2r sine theta cosine theta dr theta plus r squared sine squared theta d theta squared plus dr squared sine squared theta plus 2r sine theta cosine theta dr theta plus r squared cosine squared theta theta squared. So the term here is just dx squared, the term here is just dy squared. And when you add these together, you notice that you have some trig identities. Cosine squared theta plus sine squared theta is 1. And these terms here, minus 2r sine theta cosine theta plus 2r sine theta cosine theta will cancel. So you'll get dr squared plus r squared d theta squared. So ds squared is a distance. dr squared is also a distance. And you have an r squared here, which is distance. So the distance squared. So all the units will match up. Okay. So if we, so this is what happens on the plane. We can try to see what happens again on the sphere. Okay, and we have a triangle there. Okay, so we've got the North Pole up here, the South Pole down here. What is this distance here along the circle? Okay, so it's pi r. So if you have some angle here, theta, what's this distance going to be? Yeah. Sorry, say it. Yeah. So it's the maximum angle here will be pi, and I'll tell you what the arc that you're tending there is. Okay, very good. So if this distance is, so we'll call this distance r. R is equal to, little r is equal to r theta. So the South Pole is theta equals pi, and the North Pole is theta equals 0. And in addition, we'll have an angle along the circle. So this angle runs from 0 to 2 pi. We'll call that angle phi. So given an angle phi and an angle theta, you specify a point anywhere on the sphere. Okay? So we'll start by looking at the analog formula for distance in 3 dimensions. We have dx squared plus dy squared plus dz squared is ds squared. And it's still for polar coordinates. X will equal r sine theta cosine phi. Y will equal r sine theta sine phi. And z will equal r cosine theta. And you convert from Cartesian coordinates to spherical polar coordinates. Now we want to be on the surface of the sphere. So in order to be on the surface of the sphere, the distance of the origin always has to be capital R, because that's the radius of the sphere. Okay. So as a result, dr equals 0, since r is a constant. So let's work out dx, dy, and dz. So dx is going to be r cosine theta cosine phi d theta plus r sine theta minus r sine theta sine phi d phi. dy is going to be r cosine theta sine phi d theta plus r sine theta cosine phi d phi. And dz is going to be minus r sine theta d theta. Okay. So now let's just plug these guys into there. show in trig identities, this is going to equal r squared d theta squared plus sine squared theta d phi squared. Okay? So this will give you a way to measure distances on this sphere. So if you let r vary as well, so r is not equal to r, you'll find df squared is dr squared plus r squared d theta squared plus sine squared theta d phi squared. So this will give you a way to measure distances in spherical polar coordinates in Cartesian space. This guy is the metric on sphere. This is the metric in Cartesian space in spherical polar coordinates. Okay, so we call this guy's object ds squared, we call this the metric line element. It tells us how to compute distances between points. So in the Cartesian space, it's a function of x, y, and z. On the sphere, there's a constraint. X squared plus y squared plus z squared equals r squared. So one of these variables is redundant. If you knew x and y, you'd also know z. So as a result, the metric line element on the sphere is only a function of two parameters, theta and phi. And any point on the sphere, you specify by knowing this angle and this angle. Okay? This guy here has three parameters again, r, theta, and phi. So it's making this redundant description of dx squared plus dy squared plus dz squared. We just change coordinates, Cartesian coordinates, to spherical polar coordinates. Okay? Okay, and similarly, you can do a computation on a saddle. I won't do that since we've done this now twice. The answer you get will be so again, it's going to be a function of two different parameters, here r and phi. So previously, on some positively curved space, we had ds squared is d theta squared, r squared d theta squared, plus r squared sine squared theta d phi squared. But you'll notice that r is equal to r theta, which implies that theta is r over r. So this metric in positively curved space was really dr squared plus r squared sine squared r over r d phi squared. So you just replace the sign with a cinch to go from positively curved to negatively curved. Okay. It's the same answer. Here, this r is measured on the sphere, on the surface of the sphere. And similarly, this r
is measured on the surface of the saddle. Whereas this R is just a distance from the origin. Okay? So these R's mean slightly different things. Okay, so given these measures of distance, you can also start measuring area. You'll find there's a general formula for the sum of the angles on all of these objects. Alpha plus beta plus gamma will equal pi plus kappa, the area of the triangle, over r squared. Okay? So the angles are dimensionless. We've got an area in the numerator, so we need to have a distance squared denominator, which is what we got. Kappa is 0 or plus or minus 1, depending on whether you're positively curved or negatively curved. If kappa is 0, this term just goes away. Sum of the angles of the triangle is just pi, which is the flat space answer. Otherwise, if kappa is 1, it's bigger than pi, and if kappa is minus 1, it's smaller than pi. Okay? This parameter r is called the radius of curvature. So for a sphere, this is the radius of the sphere. For a saddle, it's basically the curvature of the saddle. Okay, so we'll notice some other things about these metrics. If you're looking at a positively curved space, looking 2 points on a sphere, there's a maximum separation they can have. For example, the North Pole and South Pole are maximally separated, and their distance is pi r. Whereas in a flat space, 2 points can be infinitely separated. Similarly, in negatively curved space, 2 points can be infinitely separated as well. Okay, so the sphere is sort of unique in it's a compact space, whereas the saddle and the flat space are non-compact. They extend to infinity. Okay? So flat space, negatively curved. These extend to infinity. Positively curved here is compact. So, we're going to call d theta squared plus sine squared theta d phi squared. We're going to call this guy, because it appears often, d omega 2 squared. So omega 2 is in reference to, so d omega 2 squared is the metric line element on a unit G squared. Okay? So you can write then the metric in flat space, ds squared, as dr squared plus r squared d omega 2 squared. So this is the metric on Euclidean free space in spherical polar coordinates. Yeah.
What's a metric?
So the metric is short for metric line element. It basically is this object ds squared thing we use to measure distances. So think about a metric as being a ruler between 2 points on a curved space. Okay, so essentially, if you take the square root of ds squared, it tells you the distance between 2 points. Just using Pythagorean theorem, basically. So you can write the metric on all our three spaces as dr squared plus s kappa of r squared d omega 2 squared, where s kappa of r is going to be r sine r over r for kappa equals +1. It's going to be r for kappa equals 0, and r sinh r over r for kappa equals -1. Now, if you Taylor expand the sine and the sinh, the leading term in Taylor expansion of sine is r over r. So sine theta is theta plus ... So these r's will cancel, and what will be left over is just r, little r. Similarly, if you Taylor expand sinh, leading term is just the argument of the sinh function. So it will be little r over big R. Big R in the denominator cancels this big R up here, so the leading term here will just be little r. So all of these terms leading order are just going to be little r. Okay? So this makes sense. If r is big, the radius curvature of the sphere is big, then for distances that are small, the Taylor expansion leading term is good enough. And you really can't tell flat space from being on a big sphere, or flat space from being on a big set. Locally, it just looks flat. We saw our experience. So if you're measuring 2 points within a city block away, it's enough to use the Euclidean distance rather than thinking about distance on a sphere. At short distances, the radius of the Earth is much, much bigger, the distances you're considering. So as a result, this is good enough to take the leading term here. So on a big sphere or a big saddle, it looks flat. Okay? So the limit, in the limit where r is much, much smaller than big R, s kappa of r will scale length r. And this is independent of the value of kappa. So I want to make one observation, which is also crucial to understanding the structure of general relativity. This observation goes under a very fancy name. It's called general covariance. But the idea is the metric line element is not unique. So for example, we wrote ds squared as dx squared plus dy squared on the plane. We also wrote this as dr squared plus r squared d theta squared on the plane. So we had two different expressions for the metric line element. But the distance is just a distance. It'll be the same whether you measure it here or there. They're just different coordinates. So the distance is unique. The distance between points on spatial slice of your spacetime is unique.
The coordinates are just something we choose for coordinate convenience. If you're working a problem in electricity and magnetism, for example, if this is you're thinking about current through a wire, you're thinking about fields a distance away from the wire, then it's a convenient choice to choose some coordinates centered around the wire. That just makes life easier for you than if you're working in Cartesian coordinates. That's just a choice. The distance is the same whether you choose to measure it in cylindrical polar coordinates or whether you choose to measure it in Cartesian coordinates. It's the same number. So, for example, the metric that I wrote there, ds squared, I could write that just as easily as dc squared over 1 minus kappa c squared over r squared plus c squared d omega 2 squared, with c defined as s kappa of r. So that's just a change in variables. That's when we write the metric in a different way. If you measure distances with this metric or distances with the metric above, I get the same answer. Okay? So you measure the same distance, and the idea of general covariance is that coordinates are labels. They have no intrinsic physical meaning. They're just a way of parameterizing the system. So in any coordinate system, you should get the same answer. And this idea also goes under the name diffeomorphism invariance. The general relativity is generally covariant theory, or equivalently diffeomorphism invariant theory, meaning that whatever parameterization you choose, you should get the same answers at the end of the day. Okay. So far, we've talked about measuring distances in space. Now the next step is start measuring distances in space-time. Okay? Yeah?
Sorry, what are the last two words right
These?
there?
Diffeomorphism invariance. It's just a fancy name for what, well, it's a name general relativists use to describe the theory. It's a symmetry of general relativity, if you like. So, you know, in electricity and magnetism, for example, there's an underlying symmetry, which is a symmetry of the circle, and that describes how you describe the redundancy in your description of the theory. So, in electricity and magnetism, the physical quantities of electric fields and magnetic fields. The way you define electric fields and magnetic fields is in terms of scalar potentials and vector potentials. Scalar potentials and vector potentials can be described in many different ways and still give you the same electric field and magnetic field, which is a physical thing. So that invariance in description of the actual physics, irrespective of how you choose to parameterize your potentials, means that potentials are somehow redundant. There are different potentials that give you the same physics that is what really you're interested in. So there's a symmetry in electricity and magnetism. The symmetry is basically the symmetry of the circle. So it's called a U1 symmetry. There's an angle that describes the circle, and that circle symmetry is the symmetry of electricity and magnetism. Similarly, there's a symmetry in general relativity. The symmetry is basically independence of coordinates. So the actual coordinates you choose are just labels. They're all physically meaningful. The quantities you compute for these coordinates are physically meaningful. The different parameterizations are basically redundant in some sense. There's an invariance that lets you choose whatever parameterization you like. Good questions? Yes.
In the first chapter, it was this one here. Is it from the concept of the R sign, R?
You asked if I'm missing something?
I'm saying where is it from?
I'm just making this change of variables. I'm defining C to be S kappa of R. And we're replacing dr with dc.
Just so, given this, I can define R as a function of C. And then dr is equal to R prime of C dc. So just plug this in, that expression there, and I'll get this. Okay, so the idea of special relativity is to put space and time on an equal footing. So space and time are mathematically on equal footing, but space and time are still somehow different in that we're allowed to move forward and backward the different spatial dimensions. We're only allowed to move forward the time direction. So space and time are treated the same, but you should still think of them as being different things. And the factor of different things is reflected in the metric line element in ordinary flat space. Measuring the distance between 2 points in space-time, t1, x1, y1, z1, and t1 plus delta t, x1 plus delta x, y1 plus delta y, z1 plus delta z, which will call t2, x2, y2, and z2. You'll plug the differences between, so this is point A, this is point B. So the distance between B and A, the difference between B and A is delta t, delta x, delta y, delta z. Measure the space-time distance between the points B and A, you plug these into here. Okay. So the distance is, so the distance in time, the difference in time between space-time points A and B, they'll enter with a relative minus sign compared to the distances delta x, delta y, and delta z, which you plug into here. Okay? So we'll see what the relative minus sign means. In spherical polar coordinates, we write the same metric as this guy here. Okay. So this is called the Minkowski metric. It corresponds to the distances on R1, 3. This tells you there's one coordinate which enters with a minus sign, and 3 coordinates enter with a plus sign. Okay, so the idea of special relativity is that 2 points in space-time, A and B, which are connected by a light ray, are at 0 distance. So you start at B, you send a signal with light to a point A in space-time. It takes a while for the light to propagate from B to position A in space. So there's a separation in time as well between these 2 points. The claim is any 2 points are connected by a light ray like this are at 0 distance. They're at 0 distance because this minus term here exactly cancels this plus term here. Okay. So these points are connected, A and B are connected by what's called a light or a null geodesic. Since light travels along geodesics, which minimize the travel time, externalize the travel time. So that's just how we set things up.
Sorry.
Yeah.
How are the 2 points, how do they have a new distance in between?
So you have 2 points. So we'll start off here. X1, Y1, Z1. You're sending a signal to a point X2, Y2, Z2. You send the signal at time T1. The signal is received at time T2. So these 2 points are separated in space-time. The claim is that the signal is light that you're sending. In the space-time distance, the distance is 0. Okay? And it's because there's a term here with the minus sign and a term here with a plus sign. So let's choose our coordinates so that theta and phi are fixed. Okay? So we're sending a signal, say, directly up. Okay? That way theta is equal to 0 and pi is equal to 0. So then the distance between these 2 points is just r in space. Okay? So 0 is ds squared, is minus c squared, dt squared, plus dr squared. Since I'm working in spherical polar coordinates, theta and phi are fixed, so d omega 2, which was d theta squared plus sine squared theta, d phi squared, this d theta is 0, this d phi is 0, so d omega 2 is 0. So the distance is just minus c squared dt squared plus dr squared. So this tells us that dr dt is, well, let me be a bit more slow about this. So I bring this to the other side. I have c squared dt squared is dr squared, which I can write as dr dt is plus or minus c. Okay? So that tells us the velocity of the photon is the speed of light, which is what we know. So velocity is the speed of light. Okay. Yes. A light or null geodesic? Okay, so we've so far just looked at distances in space-time in flat space. Okay? So now we're going to try to generalize this to curved space. So the assumptions of cosmology again are that on large scales, the universe is homogeneous, and that's the problem. So it looks the same, and yes?
In space-time, what about moving objects? Is the distance between them still zero? I mean, yes, it's still zero. Because if an object goes, you send the light, and then when it comes back, it's going to be a longer distance from where it might go.
So the distance light travels is always 0. That's just the way things are constructed in flat space here. Objects can move, and they can travel distances as they move. But light itself, each distance is always 0. So remember that homogeneous means there's no preferred location. Isotropic means there's no preferred direction. And these assumptions are operative on scales bigger than 100 megaparsecs. So on scales bigger than 100 megaparsecs, we've never measured the sum of the angles in a triangle. So we don't know whether the universe is flat, whether the universe is positively curved, or negatively curved a priori. We simply don't know. So we also know, so we don't know that spatial sections are flat. Because the radius of curvature is huge, and we wouldn't be able to tell based on local measurements. We also know the universe is expanding. Hubble's law tells us that. Distances are changing as a function of time. Because of the expansion. So two galaxies are separated by some distance today, because the expansion will be separated by a larger distance tomorrow. So, based on this, we'll just make an ansatz for what the metric of curved space should be. So, ds squared is going to be minus c squared dt squared plus, because distance is some function of t, we should include some function a of t. And then we just have the metric in the different spatial sections we looked at previously. This is the ansatz we'll make for a homogeneous and isotropic space. It's homogeneous and isotropic, which means it can only be a function of time that appears in the metric. It can't be a function of any location or any direction. So you can't single out an angle, you can't single out a distance. So whatever function appears here as a function of time has to multiply this whole thing. That's the only way to respect homogeneity isotopically. So there's some functional dependence on time, which enables distances to change as a function of time. And we don't know the spatial sections are flat, so we include S kappa of R. So this is the guess we make. It's a very natural guess that we make. So this metric, this guess, was made by Friedman, Robertson, and Walker back in the 1920s. This is called the FRW universe. It turns out this FRW universe is a very good approximation to our universe. So we're very happy with this guess. And we'll be exploring the features of this metric as we proceed. So in particular, the Einstein equation derived from this metric will tell us about the evolution of the universe. Next week, we'll look at these equations to describe the evolution of the universe. Okay. This A of t, which appears in the metric, is the same scale factor we saw previously. Okay. So we saw that H couple parameter, T, was A dot over A. So this is that A. So we've normalized things so that A of T today, A of T0, is equal to 1. The universe was, this factor here is smaller than one in the past and bigger than one in the future. Okay, so we've got this metric. We should discuss what this metric actually means. Okay, so T, the F4W metric, this guy is called cosmic time. Okay, and X, Y, and Z are called co-moving, or equivalently, R, beta, and phi. These guys are called co-moving coordinates. So what this means is that we've got some grid. So we've measured X, Y, and Z, or equivalently R, theta, and phi on this grid. So you run time, maybe I should draw this. So we have this grid. We run time. And because the universe is expanding, the grid will get bigger. Okay? So we fix coordinates on this grid. Those coordinates stay the same even as the grid itself expands. Okay? So that's what we mean by co-moving coordinates. Okay, so the point here has coordinates X, Y, and Z. This point there. And the same point P will have coordinates X, Y, and Z here as well. It's just because of the expansion, the scale factor in front has changed. So the distance is changing because of that scale factor. But the distance on the actual spatial section at a different time stays the same. Okay, so you have two different points, P and Q. So this is x1, y1, z1. Q is x2, y2, z2. This is P, this is Q. The coordinates stay the same, so the distance between P and Q here is the same as the distance between P and Q here. Distance in space-time is different because of the scale factor. Okay, so A of t, this is A of t1, this is A of t2. We changed the distance in just because this guy is changing due to the expansion. So, if the expansion is homogeneous and isotropic, then the co-moving distance or the co-moving coordinates of a point stay the same. So the assumptions of homogeneity and isotropy are crucial here. If you're stretching different parts of the space differently because of the expansion, this would no longer be true. We're assuming homogeneity and isotropy, so as a result, all the dependence is in the scale factor. So the metric then is described, metric line element. Yeah.
It's the same in both instances, but wouldn't one be scaled by a factor of a to the a function of t?
So what I'm saying is that these things are expanding. And because the expansion is isotropic and homogeneous, all the dependence on the distance between these points is built into the scale factor. The intrinsic distance you're measuring on these sections remains the same. Okay? So the distance here between these 2 points is going to be A of T1 times D of PQ. Whereas here, the distance will be A of T2 times D of PQ. So the A of T1 is smaller than A of T2. So the distance is bigger here. But the actual distance you're measuring on the plane itself is just D of PQ. And that stays the same. Okay? So metric line element then is a function of a physical constant, speed of light. It's a function of 2 parameters. Two parameters are kappa and r, the radius of curvature. And it's a function of one function. A of t. And the rest are coordinate choices, which are free to make as is convenient for us. Okay? So the only requirement is that in your coordinate system, each point has a unique length. So much of cosmology, so we know the physical constant is just speed of light. We measure that, we're done. The rest of cosmology is determined in part in figuring out what kappa is, whether we're positively curved, negatively curved, or flat. Figuring if we're positively curved, negatively curved, figuring out the radius of convergence, r. And finally, looking at what the behavior of this one function, A of t, is in terms of different periods in the history of the universe. Okay. So what we have is that C is just a physical constant. C is a constant of nature. We can't play with that. Kappa, we don't know what it is, but once we figure it out, it's set for all time. We can't have a universe just homogeneous and isotropic with kappa at one time being positive and kappa at a later time being negative. Doesn't work. So kappa has to be the same, whatever it is. It's either 0, plus 1, or minus 1, and that's it. We just don't know what it is. Okay, so then we have, so much of cosmology is devoted to figuring out what kappa is. And if kappa is non-zero, what r is. And then we're interested in the functional form of the scale factor A of t. Okay, so a few other comments. Homogeneity and isotropy require large scales. So these equations we're going to come up with are not useful on small scales. So if you're looking at the behavior of space between us and Andromeda, these equations are not the right equations to look at. These are small scale structures. We don't really understand the t goes to 0 limit. T goes to 0 limit. We know the universe is much smaller, much denser. There's a big bang that happens maybe at t equals 0. We don't understand any of that. So these equations are only operative on scales where t is sufficiently large, and we have distances that are also large. Okay, so we're mostly through. Let's take a break. Okay, so we've described the FRW universe. We've got a metric which looks like ds squared minus t squared t squared plus a of t squared r squared plus as a kappa of r squared the negative t squared. So you then start thinking about how to measure distances in this FRW metric. So the FRW metric, galaxies received from us as a function of the scale factor, as a A of t. So it's a function of time. So the trick then is to specify at which time we're measuring distances. Because it might well be the case that by the time you make a measurement, the thing is further away. Okay, so we need to figure out how to do this. So at a fixed time, if we know what time to use, then the distance is just going to be, the metric will be a of t squared, dr squared, plus s kappa of r squared to the negative 2 squared. Okay? So, what we're going to do is we're going to fix an angle, theta and phi. This enables us to forget about this pesky d omega 2 squared factor. At a fixed angle, this guy will vanish. And we'll think about a spatial geodesic. So along a spatial geodesic with a fixed angle, we have ds equals a of t dr. And we're working at a fixed time as well. Okay. So the proper distance, dp of t, we can write as a of t integral 0 to r dr, which is a of t times r. Okay. Now, we want to see how things change, and if we use okay, so what's R here? That's the next question we should ask. So what R is depends on whether the space is positively curved, negatively curved, or flat. So we had this function. We wrote the metric, for example, as ds squared is A of t squared. The c squared, 1 minus kappa c squared over r squared, plus c squared d omega 2 squared. Okay, so c was s kappa of r. So r is equal to r sine inverse c over r, if kappa is plus 1. R is equal to c, if kappa is 0. And r is equal to r sinh inverse c over r, if kappa is minus 1. So the r you use to measure the proper distance depends upon the value of kappa. Okay? So dp of t equals a of t r sine inverse c over r, a of t c, or a of t r sinh inverse of c over r, depending upon the kappa, plus 1, 0, or minus. Okay, so now, what about d by dt? dt of t. How is this changing with respect to time? So this is just dp dot. So the intrinsic distance here, we said wasn't changing as a function of time. All the time dependence is in this a factor. So this is just a dot times r. So we can write this as a dot over a times ar, but ar is just dp. So this is a dot over a dp of t. So a dot over a is the Hubble parameter. So we can also write this as h of t dp of t. So in particular, dp dot t0 is the velocity we measured today, and this is h0 dp of t0. Okay, so that's one way to measure describe distance. So we noticed one thing. We noticed that we could change the Hubble scale, the Hubble parameter, today to a distance. We take c over h0. So c's got units of velocity. The Hubble parameter's got units of inverse time. So this gives us a distance when we divide. So this is called the Hubble distance. And we notice that Vp t0, which was dp dot of t0, equals, I'm just repeating the equation here, so we should have done that. Got it? So the dp of t0 is bigger than dh of t0, then Vp is bigger than h0, c over h0, which is equal to c. So the velocity of objects at a distance larger than the Hubble distance is bigger than the speed of light. Okay? So at distances larger than dh, galaxies are receding Siri just turned on. Moving away from us faster than the speed of light. Okay, so why is this not a contradiction? Special relativity, which is supposed to tell us that nothing can move faster than the speed of light. Yeah.
It's because the space itself, special relativity doesn't put restrictions on how fast the space itself is spinning.
That's exactly right. So special relativity puts a restriction on how fast things can travel in space. Here, space itself is expanding. It turns out the space itself is expanding at a rate faster than the speed of light. That's not a problem. Okay? So there's no violation of special relativity. And if you want numbers, if you take h0 to be 70 kilometers per second per megaparsec, then d of h at time 0 is 4,300 megaparsecs. So anything further away from us than 4,300 megaparsecs is moving away from us faster than the speed of light, because of the expansion in space. Yes?
Like, I guess that distance, does it kind of set up like almost like a horizon in every direction that like cuts off any information coming in? But then if we move, like if I walk like 10 meters forward, does that move the like that sphere? So like do I lose the information 5 meters at the Hubble horizon behind me and gain it 5 meters like at the Hubble
Something
horizon?
similar happens. So if something is further away from us than this, if they send a signal to us, it will never reach us.
Okay.
Because of the expansion. But we can still see further than this distance. We see galaxies much further away than 4,300 megaparsecs.
Yeah.
That's because light is reaching us. The light was sent to us when they were much closer. Okay?
And then so does moving like move that? I mean, like very insignificantly, but
So what happens is if you put a picture, we've got some universe here. We've got two galaxies. This galaxy is sending a signal to us. At a later time, the universe is expanding. This galaxy is now moving away from us faster to see, but the signal is sent is still reaching us.
okay.
Because it was sent at a previous time. So we can see further away than this distance. But if they send a signal to us now, we would never detect it. Trust me, things get even weirder. So when we measure a galaxy, we look at a telescope, we see a galaxy. That means we know the angle theta and phi. We point the telescope at an angle theta and a direction phi, and we see our galaxy. Okay? So, we don't know the proper distance. we can measure the redshift. So we know there's certain wavelengths for the light. We can measure that wavelength in the laboratory, measure that wavelength in the galaxy that we see, we can look at the difference between the two, that will tell us the redshift. So we can measure the redshift Z. And this tells us the scale factor at the time the light was emitted. So remember, this redshift formula involved the wavelength at emission compared to the wavelength at observation. Okay, so we know some information about what the scale factor is when the light was emitted. So light was emitted at time t emission, and it's observed at time t0 today. So we know that light travels on null geodesics. So light has traveled zero distance in space-time. Okay? So let's put these pieces together. Because light travels on null geodesics, it's traveled zero distance. So this tells us that c squared dt squared is equal to a of t squared dr squared, because the angle, theta and phi, is fixed. So, rearranging terms, we have c dt over a of t is equal to dr. Okay, so let's integrate this. We're integrating from the time it was emitted to today, c dt over a of t, and then iterating r from 0 to r. So this equals r, and we need to figure out this interval there. So this is similar to our discussion of redshift from before. Let's get through it. Okay, so we want to look at C integral. So we want to figure out what this guy is. Okay, so let's look at consecutive crests for this wave that's traveling to us. So for the next crest, we have TE. Next crest comes out to us at a time lambda E over C later. And it's observed lambda O over lambda 0 over C later. Okay? This guy, dt over A of t, is also R, since these crests are emitted consecutively, and R hasn't changed very much over the emission of a single crest. Okay? So this also equals the integral 0 to R dr, which is R. Okay, so now let's look. So we know then that the integral from TE to T0 dt over A of t, that equals R, and this equals R. These two expressions equal each other. Okay, so let's be clever, and let's subtract the integral TE plus lambda E over C T0 dt over A of t from each side. takes a while to stare at this equation and figure out this is the right thing to do. But let's assume that we're clever enough and we figure out this is what to do. So now what happens? So we have the integral te to t0 dt minus the integral from te to t0 te plus n e over c t0 dt. And okay, there's an overlay here as well. So this equals the integral from te to te plus lambda d over c dt over a, because this term and this term will cancel. So that's the left-hand side. The right-hand side, we do the same thing, and we have integral from te plus lambda e over c, t0 plus lambda 0 over c, dt over a, minus the integral from te plus lambda e over c, t0, dt over a. And this is going to be integral from t0 to t0 plus lambda 0 over c, dt over a. Okay. So, this guy here will equal this guy there. After you do this trick. So let's see what this says. So we have the integral from te plus lambda e over c to te. Do I have that right? No, te plus lambda e over c dt over a. And this equals the integral from t0 plus lambda 0 over c dt over a. So lambda over c is going to be typically something like 2 times 10 to the minus 15 seconds, which is a very, very tiny number. So this equals 10 to the minus 32 inverse Hubble times. So it's very, very tiny. And Hubble time, in comparison, is 14 gigayears roughly. So this time interval is extremely tiny. So, yeah,
There's not for specific frequency, wavelength.
it's a particular wavelength. These are the kind of wavelengths we're observing.
Are they around that point?
Yeah. So we're observing visible light. So we're observing wavelengths like this. So, as a result, things aren't changing very much in this very tiny interval. You can do the interval. A is roughly constant during this time. So we have lambda e over a of te, and this equals lambda 0 over a of t0. So rearranging terms, the ratio a of t0, a of te is lambda 0 over lambda e, which is lambda 0 minus lambda e over lambda e plus 1. So I've just subtracted and added 1. Okay? But this is 1 plus dimension. Okay? So a of t0 is equal to 1 by normalization. So this tells us that 1 plus z is 1 over a of te. So you measure the redshift, and measuring the redshift, that tells us the scale factor when the light was emitted. you just add 1, take the inverse, you get the scale factor.
Sorry.
Yeah.
But that's unpleasant in that A doesn't change. But then if light comes from a galaxy far away, A would have changed at some point.
So we manipulated things so that we're only integrating from the emission of one wave crest, the emission of the next wave crest. In the time between the emission of successive wave crests, A hasn't changed very much.
But then the wavelength wouldn't have reached us at that time.
Right, so we're measuring here, we're integrating between TE and TE plus lambda E over C. Measuring here T0 plus lambda 0 over C. And we're seeing that the ratio of the emitted light to the scale factor when the light was emitted is the same as the ratio of the observed wavelength to the scale factor when we're measuring. Okay, that ratio hasn't changed. We're using that fact the ratio hasn't changed in order to express the scale factor of time of emission in terms of the redshift we measured. Okay, so the trick was to figure out how to subtract this quantity from both sides in order to manipulate the interval to an expression that we can evaluate. Okay, so suppose, for example, we measure a galaxy at redshift 2. Okay, so this tells us that A of TE was 1 over 1 plus Z, which is 1/3. So we observed this galaxy as it appeared when the scale factor of the universe was 1/3 the size it is today. So, in effect, because the speed of light is finite, as you're looking out into space, you're also looking backward in time. So you're seeing the universe as it was when the universe was 1/3 its current size. So one thing to notice is that redshift, Z, this depends on the ratio of the scale factor, then to now. It does not depend on whether the expansion is fast or slow. You don't know anything about how fast the expansion is happening. It doesn't matter how the scale factor evolves. You're just concerned with the scale factor then compared to the scale factor now. So in order to figure out how the scale factor evolves, we need to work harder. And in working harder, what this means is we just solve the Einstein equation. Okay? So essentially, what the Einstein equations tell us is there's some quantity which is geometric, and this is equal to some other quantity which is determined by the matter of the system. Okay. So this geometric quantity is basically a response to what this mass and energy in the system is doing. And conversely, the mass and energy in the system move according to the geometry and curvature of space-time. Okay? So what we have is a metric, ds squared is minus c squared dt squared plus a of t squared dr squared plus s capital of r squared d omega t squared. So this is basically telling us about the geometry of the system. Okay. So we need to take the information in this metric and compute geometric quantities. Those geometric quantities are both informed by what the matter is doing in the system, in the universe, and also they affect how the matter behaves in the universe. So these are the equations we need to solve. This equation is determined by the geometric structure and by the matter we have. It turns out that the matter we have, we divide into basically 3 different parts. There's stuff that we call matter. So this is visible matter and dark matter. So these are, again, 4% of the universe and roughly 26% of the universe. Then we have radiation, which is matter that moves at relativistic speeds. So we'll call this slow matter, non-relativistic matter. And then we have, in addition, stuff that's not matter, but this dark energy. And this is 70% of the universe. So all of these 3 things will contribute to the right-hand side of this equation. And the behavior of these things will tell us how the scale factor is changing in various phases in the history of the universe. Okay. So we'll see how this works next week. So basically, we start here, then we go here, and then we end up here. We're in this phase now.